Okay, today is the 17th of September.
You can see that. Record won't cover it.
Oh, okay. All right, let's do the area of a polar graph. And there's our function. We're going to go from theta equals A to theta equals B. And in order to do so, what we're going to do is find the area of this little sector first. The area of that little piece of the polar graph is approximately the central angle, delta theta, that's what this little piece is here, over 2 pi, that would be the whole circle, times the area of a circle. This is the fractional part that we have. The whole circle is pi r squared. So we'll sum up all these little pieces. We have n such pieces here. Pi's will cancel. The area, exact area, is going to be a limit as n goes to infinity. Of that sum, we have a Riemann sum in terms of theta, which is an integral. And this is the integral that we need to find the area of polar graphs. Okay, let's do one. Let's do a cardioid. Let's do all of theta equals 1 plus cosine theta. And let's find the area of this polar graph. Cardioid. Okay? Cardioid. It's kind of a cool word, cardioid. All right, so anyhow. So here we have our cardioid.
Yep, it's the blood. So gonna use this.
All right, this point here at theta equals this, so we got 2. We're starting at 2, 0 here. Okay. Now, we got symmetry with respect to the polar axis, and the usual thing with cosines being the even function that it is. What we should do here, we'll do half the area and we'll double it, okay? And we'll multiply by 2. So we're going to go from here to pi. All right, so 1/2, but we're going to double it. We're going to go from 0 to pi. The formula demands a 1/2, but we're going to multiply by 2. Pi, okay, r squared, 0 to pi, r squared. R is equal to 1 plus cosine, and we're going to square that. Yeah, sometimes these do get messy, I must say, but you know, it's the way it goes. 2's cancel. We have to integrate 1 plus cosine theta squared. To do that, multiply it out. Okay. Integrate each part. All right, so we're going to integrate the 1, that's theta. We're going to integrate the 2 cosine theta, that's equal to a 2 sine theta. But the cosine squared is a problem, okay? What do you have to do to integrate the cosine squared? Half angle substitution, perfect. Let me write that off to the side. Cosine squared is 1/2 the quantity 1 plus cosine 2 theta. That's the substitution you need for cosine squared. That's a Calc 2 thing. Okay. Sine squared would be a minus here. And now, everybody okay with that? Okay. And then when you integrate it, you're going to have the integral of 1/2 d theta, and that's going to be a 1/2 theta. And when you integrate the cosine of 2 theta, you have to multiply by 2. It's a cosine u form. Multiply by 2 and multiply by 1/2. So you're going to have a 1/2, the integral of cosine u, which is a sine u. Okay, so the integral is 1/2 d theta here, 1/2 theta. Then you have this 1/2 multiplied by 2 and by 1/2. I need another 1/2. I have this one, and I need another one because I got to multiply by 2 and by 1/2 again, okay, to get the du. Is everybody okay with that? Everybody all right? Okay. What I'm saying is when you do this integral, you have the integral of 1/2 d theta, and that's 1/2 theta. Then you have 1/2 cosine 2 theta. You got to multiply by 2 and another 1/2 to get the du part. Okay, because this is the u, the du is 2d theta. So I end up with a 1/2 times another 1/2, a 1/4. It's not even going to matter because when I substitute in 0, I'm going to get 0. When I substitute in pi, I'm going to get 0 anyway, so it doesn't even matter. But for the sake of being accurate, I need another 1/2 in there. Okay? And that's from 0 to pi. So we end up with pi. Sine of pi is 0 plus a 1/2 pi. A sine of 2 pi is 0 minus, substitute in 0, we get 0, 0, 0, 0. We get an answer of 3/2 pi. And that's the exact area of that cardioid. It's 3/2 pi square units. What's wrong with this, Anthony? Nothing?
Looks okay.
All right. Your face a minute ago said something's wrong here, Burns. But no, huh? All right. All right, any questions on that?
Right in the beginning for a equals 1/2 times that 2, where did that 2 come into play for?
Because I'm doing the integral from 0 to pi.
Oh,
Okay, that's only half the cardioid. There's a problem sometimes with these areas. You know, I think in your homework, they're going to ask you to find the area of one petal of a rose of, say, 4 petals. And the trickiest part of the whole problem is just to find out what the limits of integration will be. Here, let me just show you that. Okay, is everybody okay with this so far? Okay. No, so if you have a rose of 4 petals, let's say you have r of theta is equal to sine of 2 theta. And you're asked to find the area of one petal of this 4-petal rose. Okay. Sine 2 theta, you know, is a rose of 4 petals. If you start at 0, you're going to start here at 0. And if you increase to get to pi over 4, at pi over 4, you'll have the sine of 2 times pi over 4, pi over 2, bless you. And the sine of pi over 2, okay, is equal to 1. All right, so that, okay. Geez, what am I out there for? Okay, I'm sorry. Okay. At 0, we're starting at 0. Okay? So, my bad here. At pi over 4, we have the sine of pi over 2, which is 1. So what happens, as theta increases, the sine of 2 theta will increase. Okay, and we'll get out to here somewhere. When we get up to pi over 2, okay, pi over 2, this will be 2 times pi over 2. It will be the sine of pi. We're back to 0 again. Okay? Okay, it's going to start off like this. Okay? This is the sine one with the symmetry with respect to theta equals pi over 2. Okay? Okay, this would be what it looks like. We want to find the area of this one petal. And I'm going to tell you the best way to find areas of polar coordinates, generally speaking, is to find the least area necessary and use the symmetry of the situation to find the total area. And let me just give you an example. If r equals cosine theta, we know that's a circle. It's a rose of a single petal. But if you go from 0 to 2 pi, you traverse it twice, and you don't get the right answer. You take the smallest area that you can in order to do the problem. I'm going to take this area of a half a petal and double it, okay? I'm going to take half a petal. And half a petal will go from 0, okay, to pi over 4, okay? 0 to pi over 4. Pi over 4 gets me to here. So that area is 1/2. I'm going to double it because I'm going to go 0 to pi over 4. That's out to here. R squared d theta. All right, does everybody see what I'm doing here? Pi over 4 gets me to this point. I'm going to take this area. I'm finding this area right in here, half of it. You could go pi over 2 and come back to here, and that would work as well. You wouldn't have the 2 here. Okay, how do you integrate this? Well, these cancel again. Square that. How do you integrate that? Might as well do it. Let's do it. How do you integrate it? Half angle, thank you. It's 1/2. What does this become?
1 minus cosine of 4 theta.
Perfect. Very nice. Nicely done. It's a 4 theta. It's double that argument. Okay, it's 4 theta this time. It's 1/2 the quantity 1 minus cosine 4 theta. Twice whatever this is, okay? Twice what this is. If that had been sine squared theta with no 2, you'd have a 2 here. With a 2 here, it becomes a 4. So we get 1/2. Let's integrate it. You get theta. This is a cosine u form. U is 4 theta. D was 4 d theta. Multiplied by 4, multiplied by 1/4. The integral of cosine u is sine. And we're going from 0 to pi over 4. Okay? So we get 1/2 pi over 4. Now what happens here? We substitute in pi over 4 for theta. Multiplied by 4, we get the sine of pi. 0. Substitute in 0. 0. 0. The exact area of one petal of this 4 petal rose would be pi over 8. The 4 petals together would be pi over 2. Okay? That's it for areas, for polar graphs. I put my pen away like this, it means, that's it. All right, so, any questions? Yes?
The 1/2 in front of the equation, in the beginning of the integral. Yeah, where's that come from?
That comes from the derivation of polar areas of polar graphs, way back in the beginning. When we derived it, you need the 1/2.
Okay.
That's always part of
Okay,
it.
the original.
Yep.
Okay.
Any other questions at all? All right, tomorrow, here's what we're doing. I don't know what we're doing. We're doing, what's that?
Beach trip?
Yeah, wow, that is an idea. I'll tell you what, I'm going to give you a list of topics for the test. Make sure you know what to do, what I'm going to ask you. Starting with the conic sections, there's a couple things. I want you to know some. I'll go right through the list. Conic sections is a part of the test. What you should know for conic sections, what you should know for parametric forms, and what you should know for the polar coordinates. That's what I'm going to do tomorrow. I'll go through the whole list of things for you to know, and you can ask questions. Monday, ask questions, okay? Have some questions. It'd be nice if you ask some questions. Tuesday will be the test. See ya.